Hi, so I'm doing ipp3 problem 3, and so the problem breakdown. A block of mass m is attached to a string. The string is being used to pull the block up an incline at a constant velocity. Therefore, this is a net force of 0 on the system. In this scenario, the system is the moving block and the surroundings are the incline, the string, and the earth, and the rest of the area or room. The incline makes an angle of theta with the ground. The string is pulling the block at an angle that is parallel with the ground. The coefficient of sliding friction, also known as the kinetic friction in this case, is mu. While the x and the y positions are part of this scenario, the z position does not change. The goal is to determine the tension in the string while the block is being pulled. So here I have a free body diagram and this is an expanded one because as you can see I have like the dotted lines which I know are not supposed to be in the real one. But so there's a normal force in the perpendicular direction, and then there's the friction going against the motion in the parallel direction of the motion of the block. And then there's the force of gravity, which is really straight down, but then you have to break it up into components. One component is perpendicular to the block, to the surface, which is the force of the earth cosine theta, and then there's one that's parallel to the motion of the block, which is the force of the earth sine theta. And then you have the force of the tension of the string, which is being pulled, and as you can see, it creates an angle of theta again with the incline. And the contact forces in this case are the incline, which is like the wooden, and then the block, and then the string. And so to continue, the result of this is the magnitude of the force of tension is mu mg cosine theta plus mg sine theta over cosine theta plus mu sine theta. And to do this, I used Newton's second law of momentum. Since the velocity was constant, Newton's second law tells us that the net force is 0. Therefore, all the individual forces must sum to 0. As such, the magnitude of tension was solved by setting the tension equal to the other forces acting on the block. And as you can see, I have the actual free body diagram here without all the other pieces. And I decided to tilt it because the actual block is on an incline itself, so that made it easier for me to visualize which forces are acting on it and in which direction. And then as you can see here are my calculations. So Newton's second law, as the force equals mass times acceleration, and then the net force is the force of gravity plus the normal force plus the force of friction plus the force of tension. And then since v is constant, a equals 0, so the net force equals 0. So then all the forces sum to 0. And so then I broke those up into their components, the force F net x, which is just the force of gravity in the x direction, which is negative mg sine, minus the force of friction, force of the sliding friction, which is mu, normal force, plus the force of tension in the x direction, which is force of tension cosine theta. And then again, I set those equal to 0 since the net force is 0. And then I found then I summed them in the y direction, which is F net y, you can see there. And then using the y direction, I solved for the normal force, which ended up being mg cosine theta minus ft sine theta, which is, And then I was able to plug that back into the x component equation. And then I got the force of tension to be equal to mu times mg cosine theta plus mg sine theta over cosine theta plus mu sine theta. And in this case, m and g equals the force of gravity, which I think we all know. And then to conclude, the tension in the string is mu mass times gravity cosine theta plus mass times gravity sine theta over cosine theta plus mu sine theta. This makes sense because this is just the force of friction plus the force of gravity in the x direction divided by the trig functions of the angles. This makes sense because since the net force is 0, the force of tension is the summation of the other forces acting on the block. In this case, force of gravity and force of friction. The normal force is the force of gravity in the y direction minus the force of tension in the y direction. It has been manipulated and worked around, and I think part of that is what is in the denominator currently. So yeah, thank you.